We can start. Distinguished participants, distinguished visitors, I would like to welcome you all here. Together, we are celebrating the 12th Solar and Wind Energy Congress. In the previous years, we didn't have so many participation. Now we're exponentially growing, and we are hearing very happy news. And we have seen that EPDK has granted a lot of good news to the projects, and we are also catching our 2030 targets in terms of national energy projects. In 2035, we are also adding 5 gigabytes of offshore plants. In the previous years, we defined some targets, but it was not easy to catch. Our industry is taking baby steps, but we have a lot of experience and we continue with our experiences. We will be catching our targets. We have energy demands together with the growth of our country. We see a lot of energy demand, and we see a huge deficit. In this sense, balance deficit, we will be using renewable energies. The country will be using their own energy. You can see that we are going to achieve our energy independence soon. Rather than the cost of the energy, we can see that independence of the energy plays a crucial role. We have witnessed it after Ukraine and Russia war. When we see in the plans of 5-year plans, 10-year plans, these are the topics that we will be focusing on. Offshore electricity production and their transmission to the red will be one of the key points that we will be focusing on. I'll be giving the floor to Mr. Kazım. He is participating from TEYAŞ. TEYAŞ is Turkey electricity distribution. He is the coordinator of this transmission and distribution planning. We are in touch for the long years, and you are always consulting to you about the capacity, and LPGD started with the capacity building. We continue with the capacity building studies. In the period of considering the period of 10-15 years, we have some issues regarding the transmission and networking solar and wind energy. In order for us to increase our energy capacity, what can we do? Well, in order for us to increase our capacity, we need investors. We need investors for first and foremost. It is not just about the capacity building of TEYAŞ. All other distribution companies have been building capacities, but we have to talk about the allocation of the capacities and the expectation of the TEYAŞ. When we arrive 2035, it's not just about 30 gigawatts and 50 gigabytes of transmission. This is the scenario of production, but what are the challenges that we're going to face in that year? First and foremost, we have to integrate this distribution to the system. We are always discussing the storage. When we say flexibility, we are talking about storage, but it starts with the network flexibility, location flexibility, plant connecting to a network. We shouldn't really be facing with the limitations from any location with all the production facilities. We have to be able to transmit and transfer the energy with the storable and non-storable 35 gigawatts. We have to continue with the gigabytes. We have to establish the secondary and third corridors. We are considering AC, but depending on the location, we will be using HVDC solutions from the land, through the land. As we have mentioned in the previous sessions, if they are offshore plants, depending on the distance from the location, we can also use HDS and maybe HS solutions can be provided. This is the plan and the first challenge that we are facing in the decade and 2 decades, upcoming 2 decades, that transmission and conduction area. As Turkey, we have to provide the electrification of the plants, of the fossil fuel consuming plants, in the transportation industry, in any other industry. We will be talking about hydrogen as we talk about in the power stake. All of the devices, materials that are consuming electricity should be consuming more electricity. If we have an electricity based consumption, we will be having a system based on RAS in your network. Today, depending on the technologies, in order to provide the stability of the network, we have to have these conventional gas, natural gas stations. If you add more renewable energy stations, you are decreasing the conventional amount. So you can add gas and RES. So it's about the consumption. Other industries should be electrified. Maybe in plans that we have our future, we have to monitor the demand in parallel to renewable energies. We can use another some methods, other methods, different methods such as uh, with a model parallel to the consumption. It's not just about the producers and consumers apart. Maybe we can also join the actors of the players in the field. We can establish a higher level. It's not just about the allocation of the capacity of TEAŞ. Our next step should be focusing on smarter solutions, smart systems. I don't want to take much of your time. This is all I have to say in the first round. Thank you. It's really interesting as TEAŞ, as the owner of the process. It's not us to decide. Maybe we are the ones directing these demands. So I have to give the floor to Mr. Pınar, Professor Pınar, established the Department of Machinery Department in Özyeğin University. He is the director of HM. What are your activities in HM? We know these energy areas that you're working on these areas. Could you please elaborate on that? First of all, I'd like to thank you. Thanks to Turek, and as well as celebrating the anniversary of Republic, we have to take a look at the big picture. It's not just about wind energy, it's all about the sustainable energies. Well, we'll be also talking about energy islands, a cost action. Our situation is not that great. It is a warning. This is the warning that was written. It was a phrase announced by the General Secretary of the UN. The world is on highway to climate hell. You see floods and fires. It's not such a big problems, but we receive energy, solar energy. There's a reflection, and the rest is easy to manage. We can see big problems, there are big challenges, but in 76 there is an article issued by Bapsis. He is my scientific father, I may say. Since then, the world is deteriorating. But we have some social problems. Socially, we are all impacted. We have to do something. The things that we have to do have to be scientific, and we have to see the impacts in the industry. Science is detailed. I won't be elaborating this, but these are atmospheric sciences. There are a lot of things to be done because we are also issuing a lot of carbon. In order to prevent it, we have to invent technologies. Machinery engineers are making a lot of technologies, creating a lot of technologies. If we are to decrease the carbon emission by 2050, what can we contribute? Is the focus of the um, article. First, we can see the impact of solar energy and impact of behavioral changes. We have to work hand in hand. Wind, solar is taking the lead action in this change. What do we do as a center? As a center, there is a scientific aspect to it. There is an application impact to it. We are I am particularly working on thermal radiation heat transfer. If we are considering heat transfer, we see that wind is also involved in it. It is a new project. These are also new projects, a series of new projects. But we are facing a complex issue, complex problem when we talk about climate change. It's not just about wind, solar energy. If they are to impact climate change, it is not just the engineering problem. These energy islands are one of the complex issues that we have been referring to. I was in the Blue Hole. They were talking about offshore plants. It's a big challenge that we're talking about offshore plants. They have to be firm, stable. It have to it has to resist for a lot of years. Imagine this is the highest level of engineering. Then you will be carrying it to the land, or you'll be using it on the islands. They can be actual islands, they can be artificial islands. How do you connect these islands is another topic. As you can imagine, in the upcoming 3 decades, these islands will be dominant in the world, considering the 60% of the world consists of water. Engineering problems. Construction engineering problems is one of the other topics that is regarding this issue. In terms of fluid mechanisms, the wind on the islands, how can we farm these? How can we cultivate these? Wind is another issue. We have to work with the fluid mechanics. We have to evaluate the possible applications. Maybe if after you establish these wind towers, how can we retrieve these towers after they complete their cycles? What do we do with these towers, wind towers? It's not just an easy task. We have to make the life cycle analysis of it. We already know these are the wind turbines. Turbines you have to see, it's really increasing. Their size is increasing. In the islands, there is a different type of turbulence, different type of air. We have to invent new concepts. There are a lot of new thoughts about these turbines. This is a cost action plan. In Europe, it concerns a lot of countries. I am one of the representatives of Turkey. Together with Carlos and Lambis. Carlos and Lambis are executing this project. We are managing a lot of projects. There is an electricity engineering and machinery engineering and construction engineering and coordination of these engineering fields. As you can see, it's all about carrying this energy or using it in the island. Transferring, conducting this energy is a huge problem. It's not easy to connect these. So when you plant it, when you put it in any place, it will be an issue. But maybe we can install them as a package model, such as wind turbines. As do you know why? I roughly would like to show you up to 2030 we will be seeing an increase in the electrical vehicles. Imagine we need electricity, but it will be triple or quadruple times in the wind energy. If we are to harness renewable energies, it will be even more. I'm not really delving deeper into storage plants, energy storage plants. Maybe in the cost action we have a series of questions that we are asking. The first study group is directing these questions. Well, I won't be reading all, maybe you're not all interested in this. Here we have a series of questions. As a group of 50 people, we are studying on these topics. We are intending to analyze it as companies who are interested in the wind energy, as well as the companies who are actually helping the issuing of the regulations. Of course, we have to store these energies. We organized the latest meeting in Istanbul. We continue the series of meetings regarding this project. This article is about a concept paper that is focusing on an island, Crete. It is it is free. You can download it, but they have other technologies, new technologies that's issued by this group. In these islands, we will be seeing more of this excitement of these islands. Are we can we contribute to production of hydrogen in the islands? As an estimation, we can see that hydrogen can be produced thanks to the energy cultivated in the islands. So we will have the hydrogen ready for us to use. So I am also collaborating with FIBA Renewable Energy. Our colleagues are also here together with us. FIBA Renewable Energy has different implementations in Turkey. They have solar plants, wind plants. They are located in the areas close to the sea. We can conceptualize the island applications. Our center has some projects. You can download this book through their website or you can download from the QR. Let me stop here. Maybe we can continue later on. Thank you so much. That was really impressive. That the world is leading to a climate hell. That's true. In our country, we are facing floods and forest fires in Australia, in the UK. We are facing extreme conditions. In the previous session, our colleagues were mentioning that in November they have witnessed 27 degrees Celsius. We are facing climate change conditions. In order to integrate these renewable energies, we have to tackle with climate change, energy security in Ukraine and Russia, also leading us to speed this adaptation to climate change. So these turbines engineering is the highest level that we have to continue. The momentum will be rising. I did not know about this, but I'm glad to see that Turkey is also directing a lot of good projects. We have uh, Dr. Bergüzar Özbahçeci Öztunal together with us. Dear professor, you have a lot of good works on these solar and wind panels and systems. Could you please elaborate a little bit on that topic?
Süper. Kazım Bey kapandı. Sağ olun.
Çok teşekkür ederim. Well, thank you very much, Uğur Bey. Well, dear guests, welcome. I'd like to salute you all. Well, today, I think we need to talk about the offshore wind technology, floating wind turbines. We should be talking about this, why they are the future for us. As you all know, wind energy has started with the terrestrial land wind turbines, but along with the Second World War, measurements on the seas gained acceleration, and research about them were increased, and people figured out that there were more pace, there were more velocity of the wind on the sea, and the strength of the wind is correlated with the square calculation of it. That's why people mainly directed themselves on the onshore applications. So you could see onshore wind wind farm. This was actually imagined prior to 1970s, and for the first time in 1991, onshore wind turbines were erected with poles. They were fixed. And currently, till 35 gigawatts, onshore wind turbines installed power has increased. Well, but after that, as you see, well, it was initiated in Nordic countries, and the sea's slope is really soft. In kilometers away, it is still shallow. When you go further distances on the sea, it is still shallow. For that reason, fixed pillared wind turbines, wind towers, are very feasible to apply. But because of the noise and because of the higher velocity, people had to go further on the sea shores. As they get further from the shore, productivity has increased. So then these fixed pillared ones lost their affordability, and they wanted to build a floating platform in submersible platform to carry the wind towers. Well, actually, it was already used in petroleum industry, and they wanted to adapt this to the wind energy sector. And these floating structures for the, all the shore structures, I really like them because you are not very much related to the base. Floating system, rather than a fixed system, can actually make you have less effect due to the structural changes on the base, on the floor. So, like our country, many other earthquakes on countries can have less effect because of these changes on the floor. And we could also add the environmental side on this. Of course, the research are still ongoing, but when you think of the systems with cages, if the floor is also weak, systems going under the sea could be subjected to more problems or damages compared to the floating ones. Well, there is also this issue. As these get deeper, feasibility of the floating wind turbines increases, and fixed ones can lose their affordability. And when you have a look at the world seas, up to 80% depth is around 50 meters or else beyond 50 meters. And it makes the floating systems much more feasible, and it makes the systems the technology of the future. So on the right side, you could see a potential report from the World Bank. This is the offshore wind to emerging, this is onshore wind emerging markets. Well, here, as you see, in our shores, fixed capacity is 12 gigawatts, but with the floating wind turbine capacity, we could increase up to 63 gigawatts. So it is 5 times, 6 times higher than the fixed ones. So in many countries, this is the situation. And it shows Turkey, Istanbul, and Izmir, Marmara, Northern Aegean, and West Black Sea around Kırklareli. Productivity is higher, and when they are evaluated one by one, floating potential is 6 times higher than the fixed ones. This is also from World Bank. I'm sorry, a couple of slides are still in English. In the roadmap for offshore wind developments for Turkey, you could see towards 2050, floating offshore wind installed power is expected to become higher because of these reasons. And also very recently, actually this year, this study has been published, and I think this is interesting. I want you to have a look at this as well. So there was this roadmap for World Bank for Turkey. The same study has been conducted for 115 countries. When they were evaluated, some countries have further technologies, further developed technologies, but excluding these countries, they made some filtering, elimination among 115 countries based on their electricity demand, rise core, and floating potential. In order not to lose time, I'm not dwelling on the details of the rise factor. When you take this into consideration, 85 out of 115 countries were eliminated, and 30 countries have been found to be more feasible with respect to offshore wind energy potential. You could see these 30 countries on the slide, and Turkey is one of those countries in the world. And here, these 30 countries were ranked, by the way, later on, based on their offshore wind energy capacity, floating capacity, fixed capacity, and also solar energy, LCOE, and population intensity, density, and some targets. Whether the country has a target with this respect, and also hydrogen deal, whether we have a target with respect to this or not. They are all ranked, they are given scores from 1 to 4, and among the 7 criteria, maximum 28 could be reached. And this is the scores that Turkey was given underneath with respect to these targets of the wind. Turkey only has its onshore target. But as you all know, this year, Ministry of Energy has declared its 5 gigawatt target. So our score would be 3, not 2. And with respect to hydrogen, actually, we are at the stage of making plans. Country plans are going to be prepared. So I think it's going to be 3 rather than 2. So I'm increasing our score. So here you see in this ranking, we are at the 18th place. But with this increase on the scores, we will be in the top 10. With respect to floating wind potential, Turkey is a candidate to become one of the top 10 countries in this rank, and you could appreciate the importance of the floating systems. Of course, costs are very crucial. With respect to costs, people have concerns, hesitations when I speak to them. However, as you can see on the slide, this is a rather optimistic situation according to me. With the fixed and the floating cost analysis comparison on the slide, we could see the details. In the initial phases, fixed costs are way too lower. Towards 2030, there is a decrease on the cost. However, on the floating platforms, there is going to be big decrease on the costs by 2030, because as of 2027, much more commercialized, much more maturated technology will become available, and it's going to bring decrease on the cost. So if we have a look at the cost analysis of a floating wind turbine, well, actually, turbine comprises just 20% of the whole cost. If you pay attention to this red row here, this this base here brings the highest cost. It's around 30%. So for a floating wind turbine, the most critical thing is the floating platforms itself. Okay, now you can see the most frequently used platforms. There is this ballast system spars, as you see, and the other one is related to gravity and water features. The other one is related to components like TLPs, spars, TLPs, and half submerged ones, semi submerged ones. Generally, these four systems have been known so far. As of 2009, floating wind turbines have been tried, and as of today, there's approximately 200 megawatts of installed capacity is available. It is not fully commercialized, however, it is very close to be commercialized. And in Norway, in Hywind Tampen, we could see 88 megawatt value of wind turbine. This is the biggest one. And this is spar. Spar was thought to be steel normally. However, it is made out of concrete, specific to this project. Okay, I've talked about these platforms, but is there a possibility of having a different platform? Each and every platform has some disadvantages. We could talk about a lot of things, but this is the spar platforms. There are some reactions from the bottom and the head, and on the semi-submersible ones, there could be submersion reactions, and there could be some problems coming from the waves. And TLP is very feasible, however, it is not affordable. So, can we have a more stable and economic platform other than the four platforms? Well, we have developed a new platform with a project with Turkish Scientific Institute. This is Plotolia, coming from Anatolia. This is Plotolia. Well, it shows the components here, and this platform is totally submersive because we don't want effects from the waves. There are 3 floaters, and we use also the water's effects, and at the same time it is not out of fully steel body, but it has chains, so the balancing weight is out of chains like in the spar. So this is the platform that we have developed, and in our hydraulic platform, in the wave channel, we used the wind channel. We produced the wind, we produced the wave. Wave producer is our own manufacturing as well. This is regular and irregular waves, and the wind is also regular and irregular. We've tried the current spar. When we compare these two, especially with the pitch movement, we've seen that our platform moves less than the others. This is very crucial for energy generation, and on the numerical models, we made our comparison as well. So we have made our patent application, and it is really positive. So I think we're about to be given the patent. We are at the very beginning of the process. There's this availability number, as you see. This goes up to 9 to 10, but we are at 4s right now. So the thing that we developed should be also supported with bigger scaled prototypes. We've done this with low supported prototypes, but we're going to do it with bigger sized models, and we're going to develop the prototype, and it's going to be tried in this sea environment, and we're going to be monetizing this project. Well, other than this, in our institute, thanks to ISKA's contribution, we have Ruzber Research Center for the offshore wind turbines. We erected a measurement pole, and it was done in Dikili, and we're going to start the measurements very soon. And this device will be also placed in the terrestrial arena, so it will be utilized to see further analysis. So in the very beginning of my speech, I already told you this is the technology of the future for all the countries in the world. As you have seen, compared to the fixed one, in our country we have a really big potential. And if we can develop this technology by ourselves, we can actually have a chance to export this technology to our neighboring countries, to the countries in the vicinity of our country. However, this is not easy. This is not something that could be done with only a project supported by TÜBİTAK Turkey Scientific Institute. I think it requires further support because it is slowly but surely developing in the world. Because as you all know, in the EV, when an automobile is tried to be chosen, people directed themselves towards electrical cars. So if we want to do something with respect to wind turbines on the R&D, on the development, I believe we have to be focusing on floating platforms, and it should be considered as a multidisciplinary issue, and all different components like materials, construction, civil engineering, machineries, electricity, everything, every different components, every research idea should be brought together. If it happens, I think we could do great things. Thank you so much. Well, thank you so much. Yeah, you have shared our depthness, so you've mentioned 43 meters. Well, if we overlap your presentation with this, well, I actually understand something. There's this fixed wind turbines. This is not a big potential for our country. We have to go towards the floating ones, but the floating ones have their own additional cost. Am I correct? Yes, you are correct. But I don't mean that we have to have floating everywhere. We have to make the proper research based on the conditions on the floor, or the water deepness, or semi-sub immersed ones. Maybe we could have the semi ones. Maybe it could encourage people more, since floating ones are not capitalized more. But I believe we could turn this into an opportunity. Well, this should be supported by us. We should create our own technology. However, numbers, as you have mentioned, these figures show something else, because in our own seas, the floor inclination changes from 1 to 10, 1 to 1,000, because, it just after 3 to 4 kilometers, it is 100 kilometers of depth. So, well, if that's the case, fixed ones are not going to be economic, affordable, but I believe there will be some places to conduct these projects as well. So all of these things should be evaluated. This is what I believe. Okay, thank you so much. Now, if you allow me, I'll give the floor to Merdan Yeşil from private sector. Merdan used to work in TEİAŞ, and now he works in EPRA as Power Systems Director. And Pınar Hocam, Professor Pınar has mentioned energy, and with Bergüzar we talked about fixed and floating foundations. Now, in the offshore, 5 gigawatts is our target for 2030. 1 gigawatt plus installations, this is what we are talking about. So 1 gigawatt plus installations. How are we going to integrate these to our system? How should we make the connection with HCV or HDVCs? What is your recommendation? Uğur Bey, thank you very much. Well, I'd like to thank all the participants. Thank you so much. My name is Merdan Yeşil. Like Uğur has mentioned, I worked in TEİAŞ for a long time. For a year, I work in EPRA as the Power Systems Director. Like my professors have mentioned beforehand, in the grid there is a huge change going on, especially after 2010. Very big changes occurred. It is going rather complex. After 2010, grid started to evolve very severely, and it happened all around the world. Now we're talking about EVs and hydrolysis, and also on-site consumption and integrated production, PVs and wind integration, carbon footprint, Paris Agreement. There are a lot of factors, and they are forcing us to evolve in the grid. And in order to meet these needs, one way or another, we have to get use of the flexible technologies. And one of those is HVDC. So HVDC as a technology is a simple system. So it started with a journey going to Sweden in the offshore in between two countries. If there is no terrestrial wholeness, in order to provide interconnection in between these two countries, or else energy exchange could be provided thanks to this system. Well, yes, it's still in our lives. This technology was initiated with Tesla and Edison competition. Then HVDC has become much more prominent in the world. AC outperformed DC because of certain reasons. Since capex is very high, because in certain distance they could be feasible, because two different power electronic stations should be established, and those stations have their costs, and this is called as breakdown points, breakthrough point. In the past it used to be 500, 600 kilometers, but on the terrestrial applications it was reduced down to 300, 350 kilometers. There are two different technologies, HCC, and one is based on flow, the other one is based on tension, especially with IGBT technology. It's going on very well. It decreases the cost and it increases the applicability, feasibility. And in the world, HVDC transmission capacity is preferred mainly. So this is an example from Northwest China. China is a pioneering country, as you all know. Big investments could be easily made by them. With respect to HVDC, they have big investments like 3,000 kilometers, 2,000 kilometers, 8 to 10 gigawatts resources could be carried out by them. Normally they work point to point, but in recent years, China has attempted to have a DC grid in 2030, no, in 2019, and they realized this in a big success. And Japan, 50 hertz, 60 hertz, they have two different structures, and HVDC carries out these changes. This is an island country, that's why they have a different structure. Brazil is very similar to Turkey, and land HDVC application in Brazil is very common, especially with the big power plant places. Generation should be moved to the consumption areas, and in between France and Italy, there is a small application on the HVDC side, and between the continental Europe and the UK, there is a huge investment of HVDC. It's because you can't consume electricity where it is generated, or else where there is consumption, you can't easily create generation. For that reason, energy should be transferred in the long distance. An example on the right comes from Germany. Germany, as you all know, has similar electricity consumption to Turkey. On the north, there is solar potential. On the south, there is a wind potential. So consumption is out of balance, and it should be balanced. So when you have a look at their investment plan, they are going to have 3 HVDC projects. These are still ongoing. Let's come to Turkey. In our country, yes, we have a huge grid. It is one of the biggest ones in Europe. its operation and its management is not easy because you are at the very edge of Europe and all kinds of uncertainties and volatilities or interruptions could affect our country. We are connected to Europe with 3 lines and 55, 60 gigawatt of consumption with 3 lines. It is not easy to create that flexibility. Well, underneath this, there are some technical reasons, political reasons, in order not to have further connection to Europe. Well, we are not away from HVDC. For a long time, Turkey and Kyrgyzstan's back-to-back system, almost 700 megawatt capacity has been allocated and it's been commissioned very well. And last year, we commissioned Turkey-Iran back-to-back capacity application. Why back-to-back? Maybe you can ask this question. Well, we could only have a synchronized connection. For that reason, these two applications is back-to-back. What is back-to-back? Well, back-to-back is when there is DC line in between with a long distance. On back-to-back, it is back-to-back, yes, literally back-to-back. There is a short transmission line. You convert it to DC, it goes to DC, then you come back to AC. It's like frequency insulation. That's it. Frequency isolation. It is not a transmission capacity, but it is used for separating the synchronization. So if we talk about our country, like our professor has mentioned, offshore is a hot topic. Onshore is also one of the hot topics. EVs, PVs, and storages are being discussed. So what should we do? If you ask me this question, in Turkey, in Europe, Thracian region, there is huge consumption. However, we don't have a generation capacity or potential. Yes, we have natural gas power plants, especially in Adapazarı. We have power plants. However, they are not eligible to meet the needs of consumption. In Izmir, for instance, there is wind and geothermal resources in Mediterranean region along with Mersin. There are thermal and natural gas power plants. We have huge resource of production, and in the Central Asia we have PV-based production. In northern eastern Anatolia, again, we have hydraulic potential, which is very big. So it should be supported with infrastructure and it should be transferred, transmitted to West. Yes, TEİAŞ did many things, TÜBİTAK did many things. As EPRA, we also do similar things. But the most important thing is to find the correct technology to get the maximum use of HVDC to carry out the potential effects. Well, because you might create a very serious problem on the system, because 1 gigawatts of bulk power, when it is transmitted from one place to another, this is just by itself a trouble. And after carrying it from one place to another, what you do with that is another problem. So you need static analysis, the location of the grid, the selection of the location. These are really crucial. Well, in the very beginning, this is all from my side. Thank you so much.
Benimle ilgimi çekiyor. Bir önceki
Well, let's get back to the previous map. In Mersin, we have a nuclear plant located in Akkuyu. We have Turep province. It has a huge potential for the wind energy. It is really equal to offshore energy. We're talking about 10 gigawatts, 10 gigawatts of energy. Maybe we can locate 10 gigawatts of storage space in Akkuyu plus Taşeli Yaka. You can collect with HVDC. Maybe we can also transfer it to Adapazarı, or can we really get the cost? We are also taking part in this project together with Mr. Ufuk, as we have mentioned. Uniting the resource and consumption is not an easy thing to do. You cannot change the demographics of the country. You have to change the infrastructure. Taşeli project, in terms of location, is a place where they have a huge energy. We have to benefit from this location. We're talking about 10 gigawatts of energy. In this sense, we can use it N-1, N-3 method should be used while transferring this energy. You cannot use these existing structures. Maybe if it's 5 or 10 gigawatts of energy, you can conduct it through AC part. And in terms of uh, storage, TH needs a lot of investments. You can use the correct paths if you have the infrastructure and if you also have the structures in Akyaka part, HVAC will be feasible. These are the feasible locations. If you take to the further point, maybe in Europe, in any other part in Europe, you can make a location. You can connect to Romania. You can connect it. A project that's scalable can be solved through this grid strategy. You can also use these in these problems. Thank you so much. You talked about the energy demand movements. It has to be provided from renewable energy movements. Rather than this, you talk about conduction. So conducting, maybe if it falls, the whole system will be failing. These are the important points. Well, we have to know this in the problems. We have to have this horizon. Well, last but not the least, I have to give the floor to Professor Dr. Adnan Midilli from İTÜ. Apart from being part of the İTÜ, he's also part of the steering committee of İTÜ. Well, we have produced our energy. We can conduct it with HVDC, with AC, but with the concept of power to X, we can transfer it in an X form. It can be hydrogen, it can be ammonia. In terms of transforming this, what type of alternatives we have? Where can we use this hydrogen? Can we use it in an onshore plants or offshore plants? How can we conduct this electricity? How can we carry it? Do we carry it, transform it, and do we just carry the hydrogen? Thank you so much. Thank you so much for your order. Well, this is really nice that I have the floor. We will be talking about power to X. The question that you have is, I believe, is on everyone's mind. Maybe how can we transfer this hydrogen from one point to another point? Well, normally in this in this sense, what is hydrogen? We have to see what is our perception of hydrogen. In terms of hydrogen, what is the supply chain? What is the supply chain? And in this supply chain, how can we integrate these with the solar wind energy? There are different options, and there is an evaluation, technological evaluation. First of all, let me tell you this. After UNIDOCHET, we established an hydrogen R&D center in 2010. In 2015, we established Hydrogen Technologies Association in Turkey. It is in national and international level. They are operating in different levels. Hydrogen Technologies Association as a website. You can see a lot of reports and you can see a lot of things to the engineers, investors, and policymakers can be provided with a lot of information. Hydrogen can and should be classified in four branches. One, hydrogen is the raw material. Raw materials, you can produce hydrogen, but by the end of the day, so where can you use the hydrogen as a raw material in chemistry industry or fertilization? production, or maybe in methanol production, ammonium production. You can see that it can also be used in different branches of the chemistry. It's one of the raw materials we can use. There are a lot of 24 types of hydrogen. We have a lot of studies with hydrogen using the solar energy, wind energy. It should be integrated to the hydrogen plants. In this sense, hydrogen uh, since 2020 COVID-19, and we have faced Ukraine Russia war. It was a concept that should be emerging in 2030s, but now we have a tighter schedule, but we are unprepared. Europe takes the leading role. Also, we can see the leading role of the technologies of the Far East. These technologies are, some countries have been planning electricity vehicles or other concepts. Before finishing their planning, they are delaying hydrogen plants. This green hydrogen concept, decarbonization is the concept. If we have the obligation of decarbonization, we didn't have this obligation, hydrogen wouldn't be so important. You have to catch these carbon dioxide. The usage is maybe using the hydrogen as a raw material. On the other hand, maybe the hydrogen can be used as energy carrier. For example, you produce electricity, that's right. Yes, you produce electricity, but you have to facilitate the storage of the electricity. Let me tell you this. Generally, we receive, why do we need hydrogen? I produce my electricity from solar energy and wind. This is a reasonable question. So why do we need hydrogen? Why do I really transform to electricity? Why do I lose this cost? If you use hydrogen for electricity in a certain times, periods of the day, by the end of the day, if you use this hydrogen, you take this hydrogen and deliver it to the pipes where the pipes cannot be reached, it will be an advantage for us. But before that, rather than that, you can use it, the energy carrier, and provide it as a raw material. That is the important part. Use it is different scenario. We have to take the leading part in terms of production. If you have high amount of energy, you have to store that high amount of energy. Another topic is the fuel. In terms of fuel, we have the engines and natural gas. Apart from that, the batteries that for the fuels, we can see the fuels in every part. In the advanced projects, we can also use the cooling effect of hydrogen. You can see the cycle. You have to have the raw material. You need to have the resource, and then you can produce it with the electrolyzer and without the electrolyzer. In a sense, we can make it gas, maybe the biomass gas, and maybe we can also integrate with other type of energies. You can convert it from water thanks to electrolysis. With this electrolyzer technology, we have alkaline electrolyzer. I believe it is the main column of the hydrolyzer industry. Without it, the economy cannot sustain itself. Electrolyzers are in our lives. They are recently in our lives. We don't know their behavioral traits. And the alkali electrolyzers and PEM electrolyzers are commercially used, can be commercially used here in this technology. Compressing hydrogen is another issue that we have to resolve. Of course, they have to increase to some pressure. Alkaline electrolyzers have to really give some outputs. Investors are a little bit confused. What do I have to do this? Why do I have these compressors? I can have a PM electrolyzer if we are to harness wind and solar energy in the farm. If we are to use hydrogen as a fuel, we have to have this plant of hydrogen so that you can increase it to a pressure. One of them is 200 and 220 bars. If you are to use it in the buses, it increases up to 400 bars. With a small scale usage, it can increase to 700 bars. We are testing in the laboratories. Hydrogen is mistaken with the electricity. We have the electricity. Why do we need it in the vehicles? Hydrogen has a different level. Electricity has a different level. We shouldn't be confusing these two. They have their own advantages. Another one has its own advantages. It's good to know the differentiation in terms of storing technologies. We have to know the technologies as the world is looking after storing the high pressure hydrogen up to 80%. Other storing technologies, they are also using sublime technologies. In this sense, in the essence, we can say that the hydrogen system is connected together with the offshore systems. There we have a material technology. If it's resistant, you will have a profitable technology. And in the end, you can see the hydrogen, using hydrogen. I won't be delving deeper into this. It is as a fuel or as a raw material. Apart from that, it's not really profitable using other things. We have this value chain system, and the supply chain. How can we integrate it to the offshore wind plants? Yes, our professors talked about these offshore wind plants. I will be talking more about configurations. First of all, in the first phase, maybe you can take from offshore electricity, you can conduct it to the land, and you can use it in the hydrogen supply chain. Within this usage, maybe there rises a question: how can I conduct the electricity? How can I carry the electricity to the land area if I have to use it? Hydrogen systems should be used with HVDC systems. There are disadvantages to that. In the offshore area, you can see that you have to tackle with challenges of increasing the capacity in terms of operating the hydrogen plant and sustaining it. It's another issue. It is all depending on the electricity, security of the electricity of the line that is carrying this hydrogen is crucially important. In Europe, there are a lot of studies being carried out. If you take a look at the total cost in the distance of 150 kilometers in 2030 per kilograms, hydrogen per kilogram should be approximately 5 euros of cost. In 2050, it will be decreasing to 3.5 euros. This is the result of the studies. In other scenario, we can see that maybe the value chain of hydrogen can be established in the onshore areas. What happens if we use HVC instead of HVDC? then we have to carry electricity to the land area. Onshore, there are disadvantages to that, maybe in terms of cost. If in a distance of 150 kilometers in 2030, it will be costing 4.5 euros per kilogram hydrogen. In 2050, it will be diminishing to 3.5 euros per kilo hydrogen. Offshore hydrogen production is costly. According to the studies that we have that carried out in the Europe, it is more advantageous. Another important topic is the floating solar plants, floating hydrogen plants are established in offshore areas. Then arises this question, well, how do we store this hydrogen produced in an offshore plant? You can store it in an offshore plant or onshore storage plants. Then you have to construct and establish a pipeline. Do we have to send it as a gas form or a liquid form? If you can afford, you can transfer in a liquid form. If you don't have the means, you can also transfer it in a gas form. There are advantages or disadvantages to that. If we take a look at the distance of 150 kilometers, this is the cost per kilo hydrogen. There is another option to this storage. Maybe you can also do this. You have an offshore wind turbine. Next to that turbine, you can establish the hydrogen value system. They act together. In a system, and then you produce a hydrogen. You use it with the pipeline. You transfer through a pipeline. Using that pipeline is more advantageous compared to other cable systems. This is the approximate cost calculated according to 150 kilometers of a distance. In onshore areas of the European countries, the cost of the hydrogen compared to offshore HDDC HD evaluation, we can deduce that offshore hydrogen production with wind will be increasing the cost in 2030. So we will be valuing offshore more and more in the future. We will be harnessing hydrogen in offshore plants. As a result, we have two topics in offshore plants. We have to solve three challenges. One, regulations and standardization of the regulations. In order to eliminate the limitations, we have to value the suggestions. If you're considering the offshore plants, the costs are really high compared to other renewable energy resources. In order to diminish these costs, we have to do the necessary work. If you see at the end of the day, you are dealing with the sea water, which has a corrosive feature to that. It may also lead to some technical problems. It is, in terms of life cycle, it is diminishing the life cycle of the plants. Before constructing these plants, you have to do the right feasibility. You have to make the right assessments and energy analysis together with the human resources, and you have to consider all other aspects in this chain, supply chain, for example, the hydrogen supply chain. You can especially use electrolyzer. It will be also increasing the cost per 35% per kilo in terms of operation. Onshore, approximately, we can see that it adds a value by 16%. Let me put it this way. these hydrogen islands, energy islands. These energy islands maybe can be facilitating hydrogen ports. You have a long distance maritime lines. Maybe the vessels are not getting close to the ports. You can transfer through helicopters on methanol and ammonia. It can be transferred through helicopters, or maybe they need hydrogen. We can establish and construct some islands, fuel stations that is located on the sea, in the sea, so that they can consume and provide it from these models. Turkey should consider this model. In this sense, the offshore models, energy models, and establishing these plants onshore or offshore together with all the divisions of Istanbul Technical University. We are all available and ready to collaborate. Thank you so much. Thank you, Professor Adnan. These are all novelty. These topics are very new to us. Maybe this is a ridiculous question, so that we can take other ridiculous question from the audience. If we are to produce hydrogen and offshore in order for us to establish a wind plant, Mr. Merdan, we need to connect it to a red, right? Otherwise, we won't be having a functioning wind system. It won't be functioning as an island. In offshore part, we need an electricity supply. Am I right? Or after producing hydrogen, we have to maybe use hydrogen. Thank you so much for the question. That's a brilliant question. That was what I was expecting. Well, by the end of the day, maybe if you're not conducting, if you're not transferring electricity, you have to use that electricity somewhere. The best way should be carrying the energy. Hydrogen can be used as a carrier of energy. Hydrogen can be carried and produced and carried. Maybe it might be risky, or we can produce ammonium and methanol at the same place. Maybe they're capturing carbon dioxide, transferring the carbon dioxide. They can also give you hydrogen, methanol, and ammonium. The most important part is a small-scale nuclear plant. Small-scale nuclear plants should be made hybrid with the offshore wind plants in order to maintain onshore security, and using small containers of 10 megawatts or 20 megawatts. If it's below 10 megawatts, it's a nuclear plant. If it's up to 50 megawatts, these plants can be integrated to these floating islands so that we can meet the process need, as well as producing a high-level security energy production. In this sense, in our Energy Institute of Istanbul Technical University, we made a call for papers for designing of the small and medium scale of nuclear plants. That's our answer. Thank you so much.
Salondan konuklarımıza
So I'll ask our audience if they have any question. I see two hands, but can they please pass the mic?
Fatih Bey buyurun.
Merhabalar, Tekfen Yenilenebilir Enerji Çözümlerinden Fatih Can.
This is Fatih Can. Professor Midil, I have a question for you. Hydrogen molecules could be used. Can you hear me, by the way? Okay. Molecules could be used energy transmitters So from electric energy to molecules, from molecules to electric energy, when you make this conversion, what is the loss in terms of percentage? This is my first question. My second question is that it's not a question actually. I really like your idea. In the offshore, at least we could help the ship to refuel their storage. So hydrogen or methanol could be transported, and those molecules could be transmitted to the places where they could be utilized. Big tankers could be utilized as well. If it is limited to fuel consumption of the ship, the utilization area could be shrunk. So I just want to express my opinion. Okay, first question, maybe I misunderstood. I couldn't hear it very well. Okay, let me. Uh, I couldn't hear it very well. Okay, so on offshore, let's say I generate electricity from renewable energy sources and I convert it to hydrogen, and there is a loss, right? This molecule is used to transmit the energy, and then I transform it back to energy. So what is the total loss in these two conversations? Okay, now I understood your question. I'm sorry, I can't hear properly, so I'm so sorry for this. Well, under normal circumstances, your offshore power plants, you generate electricity, you transmit it, and there is only loss due to line transmission, and you use this as electricity, right, in the application. Okay. And on the other side, on offshore, you generate electricity, you convert it back to hydrogen, you transmit hydrogen. Now it is time to use it, and efficiency starts there. Till production, till generation, yes, the same unit electricity could be used, and in terms of the hydrogen and electricity, by using the same unit, there's nothing I'd like to say here, but in the application side, if you need energy, it is more productive, efficient to use electricity. But if you need fuel, I'm underlining the fuel word, it is not for electricity generation. If you need fuel or raw material, then you need to use hydrogen. That is much more efficient. Well, I'd like to give you an example which can support this. In Norway, as RES, we have a project, and we generate electricity from wind turbines, and it is transmitted to the industry area where hydrogen is utilized. Hydrogen is utilized in these regions, industry regions. Well, this is the most efficient and most feasible solution in the hydrogen utilization. Others are additional costs where we need hydrogen. It can change the additional cost. Well, let me say this as well. Under normal circumstances, this is the rather common belief, but this is wrong. We should generate hydrogen, we should transmit it. When you have a look at the transmission cost, electricity transmissions cost is lower than hydrogen transmission. So electricity, wherever you process it on board, transmit it there, then generate the hydrogen and just utilize it there. This is much more economic and efficient. Okay, there is the last question, please, at the very end, because we have to close the session for the next session. Thank you, Abdullah Görür from Vestas Wind Energy. I am the Middle East and North Africa Technical Director. Well, I have a question to Professor Adnan Midil. I'm so sorry. Well, it is just a coincidence. Can you hear me? Maybe mic is not very strong. Well, my question is that levelized cost of hydrogen, LCOH, 20, 30, 40, 50. In the region that we are located, if we have a look at the big projects, $1, 1 kilo in 1 decade, this is what the Americans say, but your numbers are 4 euros, 2 euros for 2050. So now in Saudi Arabia, they conduct neon green hydro projects, and they state that it would be less than $2.5. What is your take on this? Well, thank you so much for this question. these options that I have presented on the slide, at the very essence of these options, you would see offshore processes and the cost of the electricity. It is 50-55% affects 1 kilogram hydrogen generation. And second of all, the hydrogen electrolyzers capacity performance, this is very crucial, and it affects the cost up to 30-35%. By 2050, they talk about $1 1 kilo hydrogen and one decade. This is their estimation, this is their prediction. But let me say you this, dear friends, in 1994, we started to produce hydrogen out of nutshell, theoretical and empirical. Then alkaline electrolyzer, hydrogen generation, a lot of hydrogen generation applications. I tried them out and I was involved in the empirical trials. So it is not how it is speculated on the numbers, believe in me, because just take these numbers higher than this. These are really optimistic. $4, $4.5, $5. Well, in the offshore, by 2050, these are the targeted numbers. They are a bit higher than normal. Well, let's talk about onshore. The cheapest hydrogen, how can we generate it? Natural gas reforming processes, right? But natural gas is fossil derivatives. They emit carbon dioxide. They say we shouldn't use it, but this is the cheapest way. We are saying that let's make natural gas not green hydrogen, but greenish in between blue and green. We are saying that let's use natural gas. Why am I saying this? Because even if you use all the renewable energy sources of the world, when you use all the technologies of the world, you could only meet 30% of all energy needs with green hydrogen. There seems to be 70-75%. We still have to use fossil fuel derivatives. So, yeah, these fossil fuel derivatives should be made greenish. One of them is carbon capturing, and the other one is fossil fuel derivatives and green hydrogen, like 10%, 15%, harmonization, blending. How can we make it more enhanced? This is what we need to think about. At the end of the day, let's say you use fossil fuels and you try to make it carbon neutral. Is it green or not? But you incinerate fossil fuel, but it is carbon neutral. Is it green or not? What's going to happen? Zero harm to the environment. Well, when we use technology, when we design technology, we have to check one thing. It is to facilitate the lives, make lives easier, it is to make the life of everyone easier. It should be the very focal point of all the technologies. If we can focus on making lives of people easier, believe in me that from solar energy, $1.5 to $2, $3 kilogram hydrogen costs. This is what is predicted for 2050. So when you have a look at the chemical reaction, you separate water and hydrogen, hydrogen and oxygen. When you use the water amount, what is the cost? Is it less than $1 per kilogram hydrogen? When you calculate it, what is the number? Well, this is higher than the theoretical numbers. This is well above the higher levels. How it happens? It's because of subventions given by the states. For that reason, the number seems to be lower. Well, other than this, for a long time I've been making theoretical and practical strategies with respect to hydrogen. 4.5 would be the lowest number without any support. Well, by 2040, and cost decrease is not estimated as well. Okay, let's summarize it. Yes, we have to make the lives of people easier, and we have to be also respecting environment. We have to be eco-friendly, and it should not be against the scientific basis. Next session will start. Very briefly, please. We can't hear the question. This is water lines, and this is out of the saline water, desalination packages, and they are worked with turbines, and at the end, electricity is generated. Since there is no place to store, everywhere is bright. In Qatar, it's the same. Well, I only know about Saudi Arabia, but let me say this in summary. Esteemed guests, dear participants and policymakers, without electrolyzer, we should be focusing on hydrogen generation. No electrolyzer, because electrolyzers are energy monsters, and you're going to feel the effect in the future more and more. Thank you. Thank you. Thank you, our panelists, for your valuable contributions. It's been really productive. We've learned many great things. Thank you so much. Thank you.